Alright, today we're talking about diffraction. One simple little word, but there's a lot of physics behind it. And I apologize, today's lecture, the material we cover today is somewhat bigger and more difficult than we should really cover in one day. So pay close attention. Maybe in future semesters I'll split it up, but for now just pay close attention. This video is probably going to take a little longer than usual, and you're probably going to have to pause at a few moments and stop and think about what we've done to make sure that you don't get lost. But make sure you understand this well so that you can do the homework, you do well on the exams, and so you understand the physics. We're talking about three kind of big topics today. One, we're going to talk about what happens when you get interference from more than two slits, focusing on a thing we call the diffraction grating that has lots of slits. Then we're going to talk about the diffraction pattern you get from a single slit. Interference can cause a pattern to appear even if you only have one slit. And that's kind of weird. We'll talk about why and what it does. And then we're going to talk about the resolving power of an aperture. Basically, if my eyeball has an aperture, the pupil, my telescope is an aperture, the size of the mirror, the lens, the light first encounters. And that limits how well you can see, even if your optics are perfect and your detector is perfect. The wave diffraction of the light will limit how well you can see, and we're going to talk about that. So first let's talk about what happens when I have more than two slits. But first let's go back to two slits. So here is a picture, here's a plot showing kind of the intensity of light from a two-slit diffraction pattern that I calculated for some blue light. Well, what if I took that same double slit aperture and I shot, instead of shooting blue light through, what if I shot green light through? Green has a longer wavelength, so my diffraction pattern is going to spread out, right? So as you see right here, the blue pattern is a little narrower. The peaks are closer together than the green pattern, all right? So if I used my double slit pattern and my double slit aperture, and I saw a pattern that looked like the blue line in spacing, I'd say, oh, that's blue light. Whereas if I see a wider pattern, I could say, oh, that's green light. And I could use my two-slit pattern to determine the wavelength of the light, to measure the light. But notice, I don't have a lot of resolving power. Now, okay, pause. What do I mean when I say resolving power? Resolving power is just how well I can detect something. And it's going to mean two different things today. When we talk about telescopes and such, we're going to talk about what's the smallest sized features I can see. But for now, when I asked about the resolving power of a two-slit aperture, I'm asking how well can I determine the wavelength of the light. So this is a very different thing. I don't want to know how small of a feature I can see in a picture. I just want to know how well can I determine what the wavelength of the light is. And if you look at this, all right, notice these two patterns, they're on top of each other. They're really close together, right? So it might be really hard to tell with just a two-slit aperture the difference between these two wavelengths. So if I shot one of these wavelengths in, I might be off by, sort of this much, all right? If I go to a higher diffraction order, however, they get further and further apart. So going to a higher diffraction order will give me more resolving power. I can more precisely determine what the wavelength of the light is. Or if I have two different colors of wavelength, I'm more likely to be able to tell that I have two different colors of light rather than having them blurred together so it just looks like one diffraction pattern. So going to higher diffraction order helps me resolve things better. But if I get too far out, notice this blue peak is getting kind of almost as close as this blue peak to this green one, and so the different orders will start to mix together if I go to too high of a diffraction order. All right? I can also improve things, though, by using more than two slits. So here, for example, here's a two-slit pattern up here. Down here is a three-slit pattern. If I have three slits, it turns out when I add an extra slit, my peaks, if my slits are all spaced by the same amount, right? So I just add one more slit at the same spacing, it turns out that my peaks show up at the same angles. But in between my peaks, I get a little sub-peak. I get another little peak here. That's just what happens when I add another slit. And because I've got little sub-peak, it kind of makes these the big peaks, a little bit thinner. A little bit thinner makes it easier to resolve the difference between these two. So I get more resolving power with the three-slit pattern. If I go to a four-slit pattern, they get even narrower. And if I have a whole bunch of slits, they can get really, really narrow. So a diffraction grating is basically like a two-slit aperture, only instead of two slits, it's lots and lots of slits. Maybe you illuminate, maybe your light hits like 1,000 different slits and they all interfere. And when you do that, these bright peaks, instead of being bright blobs, they become bright, very sharp points. All right? And that makes it easier to tell the difference between these two colors of light, between green light and red light or whatnot. All right? So the resolving power, it turns out, depends on how many lines there are in our grating, how many different slits our light goes through, as well as which order we use. Now, we define resolving power when we're talking about resolving wavelength to be the wavelength we measure divided by the uncertainty in the measurement. All right? So that way a higher resolving power means I'm determining the wavelength better. All right? So the resolving power for a diffraction grating turns out to be just equal to the number of slits in my grating times the order that I'm using. All right? So that's the resolving power of a diffraction grating. Note, once again, this is not the same thing we mean when we talk about resolving power when we're talking about telescopes. Here we're talking about determining precisely what the wavelength of some light is. Whereas when we talk about telescopes, we'll be talking about resolving small features. What's the smallest thing we can see in our image? Okay, now, where do we see bright and dark fringes? Well, let's think of our diffraction grating, all right? Instead of having two slits that are emitting light now I have a whole bunch of slits. All right. If I consider sort of a two-slit, that's a very bad line. Can I erase that without having it crash? Nope, I can't. Okay, so ignore that line. And so imagine I have my screen over here, and I go off a long distance away. We saw before with a two-slit pattern that the directions where I got bright fringes was when this distance right here was an integer number of wavelengths. But note this, if I draw another line out here, all right, this distance right here is just going to be twice that distance right here. So if this one differs by 1 wavelength, this one will differ by 2. So it turns out the places that you see bright fringes, the center of your bright peak, for a diffraction grating, you use the same formula you would use for a two-slit pattern. And the places where you see the darkest, well, yeah, something like that. The point is, the places where I get the peaks is the same whether I'm doing a two-slit pattern, a three-slit pattern, a four-slit pattern, or a diffraction grating with lots of slits. The places where I get my bright peaks is the same. All right? Now the dark peaks, well, it turns out to have lots of slits. There's lots of little stuff going on down here in the bottom. And so, well, let's not talk about where the dark is, because the dark doesn't matter. The dark is this big, vast expanse. What we care about is where the bright peaks, where the bright spots form, and we use the same formula we would use for a two-slit interference pattern. Okay. Now, next topic. We're going to talk about the diffraction pattern you get from a single slit. It turns out you can get diffraction. You can get an interference thing going on, which makes a pattern even if your light goes only through a single slit. And here's why. All right, imagine, if you will, I've got a single slit. So I've got some aluminum foil and I cut a single slit in it. All right, but that single slit has some width. And so what happens is I shine my laser in here. All right, so here my laser beam is coming in. It illuminates that whole slit, and each point on my slit, each little infinitesimal point, acts like a source. So a single slit is almost like an infinite number of infinitesimal slits all packed together. All right? If I look right on axis, right, all of these guys travel the same distance, approximately the same distance once I've gone a long distance away, and I'm going to get a bright spot right on axis. But if I go off to the side, all right, each one of these infinitesimal little slits that I'm adding together to make my single slit, the light from each of them is going to travel a different distance to get off onto a screen. Okay? And so I'm going to start to see interference stuff happening. Now, when do I see bright fringes? When do I see dark fringes in my single slit diffraction pattern? Well, let's look at this, all right? I've got an infinite number of little slits that I'm adding together. So let's just look at the slit right here at the bottom and compare that to the slit right up here at the top. All right, so let's call this distance delta S. So I go off at some angle theta off to my screen, all right? And I say at that angle, well, that angle right also shows up here, right? And so if I look at the contribution of light from just the very bottom of the slit, and I compare that to the contribution of light from the very top, they travel a different distance. The difference in their path is, once again, if I call the size of my slit A, this distance right here is just A sine theta, right? Now, what do I want that distance to be in order to get constructive interference? What do I want it to be in order to get destructive interference? Well, let's imagine that that distance is one wavelength, all right? Will that give me a bright peak or a dark peak or something in between? Your first instinct is probably to say, well, if the light from this part of my slit travels one wavelength further than light from this part of my slit, they're going to get there in phase and you're going to expect something bright, right? Well, that's where you're wrong, okay? Because, okay, totally weird, right? This distance right here is one wavelength, but I get a dark fringe in that direction. Why is that? That's because I've only considered two little pieces of my infinite number of little infinitesimal slits I'm adding together, all right? If these two are exactly in phase when we get to our screen, then this one is going to be exactly out of phase with one right in the middle, right? So if you look at this ray right here, this distance right here is going to be half a wavelength. So this will be 180 degrees out of phase with this. All right, if I go up and find a slit a little bit higher, there's a corresponding little slit up here that's 180 degrees out of phase with it. So light from this part of my slit will interfere destructively with light from this part. Light from this part will interfere destructively with light from this part. Light from this part will interfere destructively with light from this part. And if this distance is one wavelength, it turns out for every point down here, there's a corresponding point up here that cancels it out. So for a single slit pattern, it turns out that when A sine theta is equal to m lambda, that's precisely when I have matching pairs of points on my slit that cancel each other out perfectly. So this is actually the condition to get a dark fringe. So if I have a double slit pattern or a diffraction grating or a triple slit pattern, whatever, this, I would write an equation like this, only instead of A here, I'd have D, the distance between my slits. And I would look at this and I'd say, that's when I get bright fringes. But when I'm considering a single slit of thickness A, this equation tells me where I get dark fringes. All right? So where do I get bright fringes? Where do I get dark spots? I get dark spots when A sine theta is equal to m lambda. If that's where I get dark ones, where do I see bright ones? Well, it turns out it's harder to make a simple argument like that. And the bright fringes actually appear somewhere between the dark fringes, but it's not exactly halfway in between. So I'm not going to give you a simple equation to find out where the bright fringes are. But this equation will tell you where the field goes to 0 in the diffraction pattern for a single slit. All right? Okay. So here's an example. Here I have a single slit, and I've done a calculation of light passing through that slit. Here the wavelength is 5 times the size of the aperture. So where do I get dark fringes? I get dark fringes when A sine theta is equal to m lambda. All right? But lambda is way bigger than A. All right? So there's no angle where I get a dark fringe. I get light coming out in all directions. But if I make the wavelength shorter, all right, you can start to see right out here there's a dark fringe. Okay, right in that direction. Let's see. Look at our equation. A sine theta is equal to m lambda. If I set m equal to 1 and a is equal to lambda, then right at 90 degrees is right when I'm starting to get my first dark fringe. All right, so if I make the wavelength equal to a over 2, then I get a dark fringe kind of out like going in the 90 degrees direction, and I get dark fringes out here, right? A sine theta is equal to m lambda. If m is equal to 2, then m lambda is just a, and I get my one at 90 degrees again, but I also get my m equals 1 dark fringe as well. And if lambda's, the wavelength's equal to half the aperture, and so forth, I get more and more dark fringes. Notice something interesting though, right? Unlike our two-slit pattern, where I have a bright fringe, and then I have another bright fringe, and I have another bright fringe, with my single slit pattern, I have a bright fringe, but then the next fringe isn't quite as bright. But I do go all the way to 0 in between them, all right? So our logic and reasoning help us find the zeros, and we know it gets brighter in between the zeros. But as you move off to the side, the bright fringes get dimmer and dimmer. All right, and here's when the wavelength is 1/10 of the aperture. We're starting to get into the regime where ray optics are okay, and we can forget about the wave stuff, and it almost looks like our light's just traveling like a beam. We're just casting the shadow of our aperture. All right? Okay, so that's a single slit diffraction pattern. Now for something completely different. We're going to talk about our third topic, where we talk about limitations on what we can resolve with telescopes. And why is this completely different? Because I'm using resolving power, I'm using that term, but remember, I'm using it differently now. So when I talked about the resolving power of a diffraction grating, I was asking how well can I measure, how precisely can I measure the wavelength of light. When I talk about telescopes, I'm going to ask, what's the smallest size thing I can see? And rather than saying something like I can see something that's a millimeter big or whatever, normally we talk about it in terms of angle. What's the smallest angular size that I can see, right? So if I have something a meter away from me and my telescope can, measure something that's a micron in size, I would say the resolving power is 1 microradian, all right? Okay, so what determines the ultimate resolving power of a telescope or a camera or your eyeball? All right, there are a lot of things that can limit your resolution. One is maybe your detector's not very good. Maybe I have a camera and I've got a great lens on it, but the pixels in my detector are far apart, right? And that limits what I can see. Okay, but that's a technical problem. I could improve that. I can put more pixels in, all right? Maybe my lenses aren't so great. Maybe they've got some aberrations. Maybe they weren't made right. That's a technical problem that I can fix. So now imagine the ideal telescope, the ideal camera, all right? The ideal human eyeball, where everything is made perfectly. It turns out you still have a limitation, even with perfect optics, due to the diffraction of light, due to the wave nature of light. And if you make your optics so good, maybe they're not perfect, but they're so good that there's no point in making them better because you're already limited by diffraction. That's what we call diffraction-limited optics. It turns out a healthy human eye is diffraction limited. Nature makes your eye as good as physics allows it to be. I find that pretty incredible. But let's find out what that limit is. And where does that limit come from? Well, your eye has a two-dimensional aperture. A telescope has a two-dimensional aperture. But just to simplify things, let's imagine a one-dimensional aperture, because we know about the diffraction of light through a single slit. So imagine, if you will, I look at a star, but I put a slit. Instead of having I have a telescope, okay, and it's got this big round mirror, big round opening to my telescope, but I'm going to put up some cardboard, and I'm going to only let light come through a slit. Maybe that slit is 1 millimeter or 3 millimeters thick, or whatever I set it to, all right? So now, this star is way far away. It's a really tiny angular size. So it ought to make just a little blip on my detector, but it doesn't, because the light coming from my star diffracts through the slit, through the aperture, all right? So imagine I have a star here, and I make a single slit diffraction pattern. This green light here shows the diffraction pattern for my star. Now, I'm drawing it in green, not because my star's making green light, all right? It's just so that you can see two different plots. So one star is represented by the green line. Now imagine I have another star that's off at some other angle. It's going to make a spot somewhere else on my detector. But instead of making a really tiny spot, it makes this pattern here because the light diffracts through my telescope, all right? Well, I can't tell which light came from which star. On my detector, I just get total intensity, all right? And so here's the intensity of the two of them combined, all right? And so I look at this on my detector and I say, wow, these stars really aren't that big. I see kind of a blurry blob here, right? This is plotting intensity as a function of position as I move across my detector. And I see, oh, the intensity goes up over a big range. So if I look at my picture, it's going to be like, there's a star here, and there's a star here. And I know those two stars aren't really that big. They're just blurred because of diffraction well, I guess this is diffracting in one dimension, right? Because we're doing a one-dimensional problem, all right? But the point is, my stars look bigger than they are just because it's blurred by diffraction through that slit. Well, what if these two stars were really close together? If they're really close together, the diffraction patterns kind of blur each other, and I might look, and it might look like I'm seeing just one star right there. All right? Now, if I have really good signal to noise, I might be able to zoom in on that peak really closely and see there's a little dip in it, and I'll say, oh, that's really two diffraction patterns on top of each other. There must be two stars. But if I have any sort of noise, then it's going to be hard to tell that I have two stars unless they're far enough apart. So the diffraction is now limiting the resolution of my telescope, how well I can see things. All right? Okay. Rayleigh's criterion. So Rayleigh's criterion is just sort of a rule of thumb that says if your two things you're looking at are far enough apart such that the peak of one of them falls at the minimum, the first minimum of the other one, that ought to be pretty easy to resolve, right? So with my with my going through a single slit in, kind of my one-dimensional telescope aperture, when I just resolve two stars, it would look like this. And there's a big enough dip that I ought to be able to tell that it's two stars. So remember, Rayleigh's criterion is really a criterion. It's a rule of thumb. If I have a really good signal and really low noise, maybe I can resolve things that are closer together. If things are really, really noisy, then maybe I can't even resolve things that, according to Rayleigh's criterion, I should be able to resolve. But the point is, it's really hard to beat Rayleigh's criterion by much, because as they get closer and closer together, right, that dip gets smaller and smaller really fast. So Rayleigh's criterion is a very good figure of merit to tell you how small of a thing you can tell with your telescope. Now, of course, a real telescope does not have a one-dimensional aperture. It doesn't have a slit. It typically has a round-shaped aperture. So if you do two-dimensional diffraction, which we're not really going to do in this class, you can figure out what the diffraction pattern of a round circle is. And it turns out, when I calculate it, it looks like this. All right? It's kind of a blob with some rings around it. Okay? And if you take a slice through the middle, it looks something like that. All right? This is known as the airy disk pattern. It's the diffraction pattern of a circular aperture. And that's what we get on our telescope. And that's what limits the resolving power of an ideal telescope. All right? Now, it turns out if you take the mathematical form of your airy disk here, the diffraction pattern of a circle, and figure out where that zero forms, you can find that the angular size of the smallest thing you can see with your telescope is just 1.22 times the wavelength over d. Where did 1.22 come from? Well, it's really not 1.22. It's this, infinite irrational number. I believe it's irrational, truncated to 3 decimal points. It comes from the equation that tells you what that diffraction pattern looks like and where it goes to zero. It turns out you get something called a Bessel function, and this is a zero of a Bessel function. All right? But the 3 significant digits, and the zero of that Bessel function is 1.22, and this is the equation that will tell you what you can see with an ideal telescope. So if you look at this, you say, wow, if I want to see some really small object out in space, I either need to use a shorter wavelength, right, or a telescope with a bigger diameter. So there's 2 reasons to try and make telescopes with bigger diameters. One is you capture more light, right, so you can see fainter things, but also Rayleigh's criterion tells you you can resolve smaller things with bigger telescopes. So that's why astronomers like to use really big telescopes, for those 2 reasons. All right? Okay, that's what you need to know for the homework, for the exams. But I'm going to tell you more than you need to know. There's some really interesting things that might help you understand this better and do better on the homework, but it's not technically required for you to know. So here we go. I'm going to show you more than you need to know. First of all, I want to do a comparison of a two-slit and a single-slit pattern. This actually might help you on the homework, but you can figure it out yourself if you don't want to watch this. But I'm going to show you. So imagine, if you will, I have, this is what I'm plotting right here. Up here above, I've calculated a single-slit diffraction pattern. And here I've calculated a two-slit diffraction pattern for infinitely thin slits. All right? And I've calculated these two such that the distance between these 2 infinitely thin slits is the same as the width of this one slit. All right? So I'm comparing a two-slit pattern with the same spacing between the 2 slits as the width of the single slit. Now it's kind of hard to see. You get the bright maximum, and then you get a dark, and then you get bright again, then dark. It's kind of hard to see these sub-maxima over here, so let me actually plot the intensity as a function of position. You see it goes down, goes to 0, comes up again, goes back to 0, comes up, and so forth. All right? You will notice, all right, remember, for a single slit pattern, we use the equation A sine theta is equal to m lambda. Sorry, I don't have a lot of space here. And that determined where the dark fringes were. To determine where the bright fringes were in a two-slit pattern, we use the equation d sine theta is equal to m lambda. So if I have a single slit pattern where A is the same as D for my double slit pattern, these two equations will be satisfied at the same angles, but for the single slit pattern it tells us where to find the dark fringes, whereas with the double slit pattern it tells us where to find the bright fringes. So you see where a bright fringe is here, there's a dark fringe. Where there's a bright fringe, there's a dark fringe. Alright, with one exception, right on axis, both of them are bright. So that tells us, alright, so kind of the size of these blobs of light, these interference fringes for a single slit pattern, they're about the same as the size for a double slit pattern, right? Because the zeros are kind of spaced by the same as the bright peaks are here. With the exception of the middle one, right? Because I have bright on axis, but this doesn't go to 0 until I get to the next bright fringe in my double slit pattern. So in a single slit pattern you have the central blob, which is twice as wide as the other blobs in angle. Okay, now when we were in class looking at a double slit pattern, it didn't look much like this. It looked kind of like this, but with some other overriding larger scale feature on it. Why did that happen? Well, that's because the double slit pattern that I illuminated in class was not made of infinitely thin slits. The slits actually had to have some width to them to let some light through. So imagine that I make a two-slit pattern, but my slits aren't infinitely thin. For example, I'm going to show you a calculation where I assume that the slit separation is 4.4 times the width of the slit. So the slit separation would be center to center of my two slits, and that separation is going to be 4.4 times bigger than the width of my slits. What's going to happen? Well, here is a calculation I did of what a single slit will make, all right? And here's a calculation of what you would get if you had these two slits but they were infinitely thin, all right? An infinitely thin slit scatters light in all directions, right? If we look at a single slit interference pattern and the limit as the slit goes to 0 thickness, right, it spreads equally in all directions, all right? But if my slits have width, each of those slits is going to make a pattern like this. So each of those slits individually will make a pattern like this, so I get light like this on my wall. But then when I put the two of them together, those two will interfere with each other, all right? So I'll get something like this, but my interference starts with light that looks like this, so I'm really going to get the product of these two shapes, all right? So if I take the shape of the pattern I get from a single slit and compare that to the pattern I would get with, and here's the pattern I get with two infinitely thin slits, all right? So to get the pattern I would get with two slits that were this thick but spaced this far apart, I just multiply these two functions together and I get something that looks like this, all right? Plotting it, there's my plot. All right, so notice, this looks more like what we saw in class. We saw some fringes, but they disappeared, and then they came back, and they disappeared, and they came back, and so forth. And that's why, all right? It's just the product of my two-slit pattern times by the individual single slit patterns that the two of them are making. Here's another example. Imagine I did an aperture that wasn't a slit. Maybe I made a llama-shaped aperture. I know how to calculate what interference pattern you get, and it looks like this. But what if I had two llamas? Well, I just take this and multiply it by the two-slit pattern, right? Each llama makes something like this, and then they interfere like a two-slit pattern. And so here is the two-llama interference pattern, or diffraction pattern, whatever you want to call it. Okay. Now, more than you need to know about resolving power of telescopes. Let's just do a little toy problem here. Let's figure out what can a spy satellite resolve, right? Rayleigh's criterion ought to give us some insight into what the government can do with their spy satellites, all right? So, you want your satellite to be as close as possible to the Earth, right? So you can see better. Because Rayleigh's criterion gives you an angular size, but that, you know, angular size matters more if you're closer, all right? So let's assume that the satellite is as close as it can be without falling out of orbit very quickly. So low Earth orbit is about 300 kilometers. Below about 300 kilometers, There's enough air left around that there's drag that brings your satellite down quickly. All right? Okay, how are we going to get this satellite into space? Well, maybe we use a Delta IV rocket. All right, that's a big rocket. The maximum payload size it can bring up has a diameter of 5 meters. So let's assume that our mirror fills that space, and I've got a mirror that's 5 meters in diameter. All right? Shorter wavelength gives us more resolving power, but it turns out there's very little ambient light in the X-ray and deep UV bands. And there's also strong atmospheric absorption below 300 nanometers, although there's fairly good transmission for visible light through the atmosphere. So let's assume, if you will, that we're going to be using light at 300 nanometers. That's the shortest wavelength that seems practical. And let's assume our mirror has a diameter of 5 meters, and let's assume that it's 300 kilometers away. Okay, so Rayleigh's criterion says the sine of the minimum thing we can resolve is 1.22 times lambda over d. All right, but we're going to put in 1.22, and lambda is going to be 300 nanometers, or 300 times 10 to the minus 9. And we're going to divide by a diameter of our telescope, which we said would be 5 meters. All right, so let's pull up Python and load up math, and I'm going to say, so my resolving power, call it theta min, is going to be the arc sine of 300 times 10 to the minus 9 divided by 5. All right? And so my minimum thing I can resolve is an angular size of 6 times 10 to the minus 8 meters. All right? Or about radians, or about 60 nanoradians. All right? Okay, that's the smallest thing I can see. Well, notice if I'd gotten rid of the arc sine, if I just take 300 e to the minus 9 divided by 5, I get about the same answer, all right? This is a really small angle, so the small angle approximation works well. Anyway, what's the smallest size of things? So that gives me the angular size. So here's my spy satellite, and it can see something which is big enough that its angular size is theta min, all right? But if my distance here, what did we say it was? 300 kilometers? This is 300 kilometers. And this is the size of the thing I can see. Let's call it h. What is h? Well, h over 300, let's call it L. I don't want to be in the good habit of not plugging in numbers too soon. So h over L is just the tangent of theta min, which this is a really small angle, so tangent and sine are both about equal to theta min, all right? So the smallest size thing, h, is just going to be L times theta min. So let's plug that into my calculator. So 300 kilometers, so 300 times 10 to the 3 times theta min, that's 0.018 meters, or about 1.8 centimeters. So that's what Rayleigh's criterion says we can see with a spy satellite using the parameters that we thought were reasonable. Okay? So about 2 centimeters-ish. So can you read a license plate with a spy satellite? According to this, probably not. You'll probably be able to resolve the individual numbers on a license plate as blobs, but not be able to maybe tell what the numbers are, but maybe kind of close, right? Can you read a newspaper? Probably not. Okay, but could it be better than this? Maybe they're using some tricks that can help things. There's a thing called synthetic aperture radar. They put up radar satellites, all right? And radar uses radio waves, which are much, much longer wavelength in power. But they do this trick where they illuminate the Earth with the radar, and because they're controlling the radar, they're using coherent radio waves, they can actually capture images as the satellite moves and keep adding to their picture. So as the satellite sweeps out a big distance, it's almost as if they had a telescope lens that was that big. All right? And so they can use that to get better resolution. All right? But you have to do that very, very long to get any decent resolution with radio waves, because radio waves are long. Could you do that with visible light, a visible analog to synthetic aperture radar? Well, remember, to do this, you have to emit and detect coherent light, because Rayleigh's criterion is about interference, right? It's a diffraction pattern. So in order to take multiple images, right, as your satellite moves and combine them together to get better resolving power, you have to actually control the phase. You have to measure not just the intensity of the light, you have to measure the phase of it, all right? So that means you have to illuminate with a laser. That's going to take a pretty powerful laser, I think, to do anything interesting. But the other problem is your detector has to not just measure the intensity of the light coming back in your picture, it has to measure the phase of the light, which is really hard to do. CCD and CMOS detectors do not detect phase. Maybe by doing some sort of interference thing, you know, where there's some of the light they send to the earth, some of it they send straight to the detector. Maybe they could do something like that, but that sounds really hard to me. I don't know if they're doing that. Another idea is maybe I could have multiple spy satellites working together. It turns out when people do radio astronomy, when they look at the radio emissions of stars and galaxies and whatnot, since radio waves are so big, it's hard to get good resolving power with just one radio dish. So they'll put radio dishes spread out over miles and miles, and they'll combine the images together. But once again, to make that work, those images have to be added together coherently. You have to add together not just the intensities you get. If you add together the intensities, you just get the same thing that you started with. But if you know the phase of the light hitting each point in your image, you can do that. And with radio waves, they oscillate slowly enough that we can measure the actual phase. We can measure the actual wave, and you can do this. Doing this with light is really hard because we can't detect the phase. One thing you could do is you could channel the light from your two telescopes together and make them interfere. They actually do that at the Keck Observatory on top of Mauna Kea in Hawaii. They have two telescopes, and they send the light from both of those telescopes together, interfere them together to get a better resolving power. So a resolving power comparable to, you know, where your D would be the distance between the telescopes rather than the size of the mirror of an individual telescope. But to make that work, those two telescopes cannot move with respect to each other by more than a fraction of a wavelength. So maybe the military has a way of beaming light back and forth between telescopes on different satellites and keeping those satellites positioned to within a fraction of a wavelength. Sounds really hard to do, although scientists are trying to do something similar to measure gravity waves, so maybe it's possible. Another option is maybe they have bigger mirrors. We limited ourselves to a mirror that was the size that you could mount in the Delta IV rocket, but maybe the mirror is in pieces. A scientific telescope that's being developed is the James Webb telescope. It's going to be the successor to the Hubble telescope, and it's actually going to have mirrors that's in pieces that will assemble together. Now you have to assemble them very carefully and align it very well, but maybe the military have mirrors that fold out and then can be much bigger than 5 meters in diameter. So maybe then with something like that you could read a newspaper. That seems totally realistic to me. But another thing you can do is you can move your telescope closer. Instead of putting it on a satellite, we saw in the news recently about this dirigible, this blimp that the military had lost. So they got these blimps up. They're not quite out in space. They're just high enough you don't notice them up there. Much, much closer than a satellite. So maybe something like that is getting images where they could maybe read your newspaper and see what you're reading.